All right, here we are ready to tackle another calculus problem to get ready for the fall semester exam next week. So we've got this question. This is a data table, and this is intended to be a calculator active question. So feel free to use your calculator if you would like. Particle A is moving with velocity modeled by a differentiable function v sub a of t. Selected values of v sub a of t are given in the table above. So I want to remember that differentiable means that the derivative exists everywhere and that the function is going to be continuous. Now, all we have are some data points. We don't know for sure what the function is doing in between these points. I know some students like to plot the points and then kind of get a sense of what the graph looks like, and that's good. There's nothing wrong with doing that, but you need to keep in mind all we know are these, 6 points. You don't necessarily know how the function is behaving in between, other than however the function behaves, the derivative is going to exist everywhere, so no sharp turns, no vertical tangent lines, and the graph is going to be continuous. So let's start this. Part A, estimate the acceleration of particle A at time t equals 9 seconds. Show the computations that lead to your answer. Be sure to include units of measure. Well, what do I know about acceleration? I know that acceleration, a of t, is the derivative of the velocity. Now, using the notation here, we're using capital A to indicate particle A. So we're using v sub capital A. So I'm going to use little a sub capital A. And that's maybe a little bit awkward, but I want to indicate that this is the acceleration of particle A equal to the derivative of the velocity of particle A. Well, how on earth am I going to find the acceleration of particle A at time t equals 9? I know that that is the derivative of the velocity, but I don't have a function for the velocity. I don't have something that I can actually take a derivative of and evaluate at t equals 9. The key to this problem is realizing that they've asked you not to determine exactly what the derivative is equal to, but approximately what the derivative is equal to. Well, we remember that the derivative is the slope of the tangent line, and what we would do way back in the beginning of the course is you approximate the slope of the tangent line by finding the slope of the secant line. So one more time, what we want is the slope of the tangent line. We're going to approximate using the slope of the secant line. Slope of the secant line means you need 2 points. I'm approximating at time 9, which is conveniently located in between times 5 and 13. At each of these times, I know the velocity, and so what I can do is I can find the slope of the secant line that connects these 2 points, and so that'll be v sub a of 13 minus v sub a of 5 divided by 13 minus 5. V sub a of 13 is 6. V sub a of 5 is negative 1. Over 13 minus 5, we're going to get 7 over 8. 7 over 8 is the slope of the secant line, which means that that is approximately equal to the slope of the tangent line, which is the acceleration that we were looking for in the first place. Now, before we leave this problem, we also need to indicate the units. Well, what is it that we're measuring in the numerator? We're measuring the velocity of the particle, and that's being measured in meters per second. What are we measuring the denominator of this fraction in? Well, the 13 and the 5, that represents seconds. So the units are going to be meters per second, or if you would prefer, meters per second squared. You would get 1 point for showing this difference quotient and 1 point for coming up with the correct units, for a grand total of 2 points. Not too bad. Let's check A off the list. Moving on to part B. What are we asked to do in part B? In part B, for the time interval 0 less than or equal to 2 less than or equal to 32, identify the minimum number of times that particle A comes to rest. Identify all subintervals in which this happens. Well, the thing that we need to know is that if we're talking about the particle coming to rest, it means the velocity, so the velocity of particle A has to be equal to 0. At first glance, you might look at this and say, okay, well, I don't know what the velocity of particle A is. I don't have an equation, I don't have a graph. All I have are these data points. But there's something that we learned way back in the very first unit that says there is a way to analyze these data points to determine if the velocity or if the function is going to be equal to 0. And that was called the intermediate value theorem. The intermediate value theorem says if we know that the velocity is positive at some point and the velocity is negative at another point, if the function is continuous on that interval, then the velocity is going to be equal to 0. So let's scan the data. Where do we expect that the velocity has to be equal to 0? Well, here the velocity is -5, here the velocity is -1. Does the velocity have to be equal to 0 between these two places? No. But how about between 5 and 13? The velocity is -1 at time 5. The function is continuous and the velocity is 6 at time 13. 0 lies in between those numbers, so the velocity will have to be equal to 0 between 5 and 13. Continuing to scan the data, I see again that the velocity changes from positive to negative. So let's write this up. But we want to be careful. If we're going to use the IVT, the function has to be continuous. So be sure to mention that. Since v sub a of t is differentiable and therefore continuous, the IVT applies. Well, what were the intervals I was interested in? We know that v sub a of 5 is equal to -1. The velocity of the particle at time 13 is equal to 6. -1 is less than 0, which is less than 6. Therefore, the velocity of the particle is equal to 0 at least once on the interval 5, 13. We're going to continue that analysis and we're going to say, okay, the velocity of particle A at time 22 is 2. The velocity of particle A at time 32 is -3. We want to be careful now. We know that 0 is in between these two numbers. I need to write this up without telling a lie. -3 is less than 0, which is less than 2. Therefore, the velocity of particle A equals 0 at least once on the interval 22, 32. Therefore, particle comes to rest at least twice. Oh, sorry. Particle comes to rest at least twice on the interval 0 less than or equal to t less than or equal to 32. I think the way we scored this was 1 point for stating that the function was continuous and that the IVT applies, 1 point for stating that the particle comes to rest at least twice, and for all of this work in between that supports your work, we're going to say that that was a 3rd point. So altogether, this is a 3-point question. And I know based on where we are in the course, it's been a very long time since we've done any of these write-ups for the intermediate value theorem. There once was a time we were really good at that, and so this is a really good problem to refresh the skills. Let's cross B off the list. All right. Part C, this one was just made up specifically for this video. Explain why the acceleration of particle A must be equal to 3/4 at least once on the interval 0, 20. This one, I would assume that when you worked on this problem on your own, maybe you weren't 100% sure what to do. Well, I want to know that the acceleration is equal to 3/4 on this interval 0, 20. I want to show why that's true. Well, here's the important piece. We've already established and used this fact a couple of times. The acceleration is the derivative of the velocity. I want to show that the derivative is equal to 3/4. Well, problems that require me to make statements about the derivative of a function always get me to think about the MVT, the mean value theorem. In order to apply the mean value theorem, you need to tell me two things. Number one, the function v sub a of t has to be continuous. Well, we were told that in the beginning. It has to be continuous on the closed interval 0 to 20. The second thing is that your velocity function is differentiable, this time on the open interval 0, 20. Therefore, the MVT applies. I need both of those pieces of information to be true. The velocity function is continuous on the closed interval. The velocity is differentiable on the open interval. Both of those are true, so the mean value theorem applies. Let's keep going. The mean value theorem says if I find the slope of the secant line that connects those endpoints, that it has to be equal to the slope of the tangent line somewhere in that interval. Well, if all of this represents the slope of your secant line, the velocity at time 20 we can see is 10. The velocity at time 0 is -5. Your denominator is 20 minus 0. Doing the computations, we get 15 over 20, which is 3/4. What this means, we can say, therefore, v sub a prime of t equals 3/4 at least once on the interval 0, 20. That's what the mean value theorem promises us. If your function is continuous and on the closed interval and differentiable on the open interval, then the mean value theorem says the slope of the secant line will be equal to the slope of the tangent line at least once on the interval, and that's exactly what we were trying to prove. At this point, I'm going to pause the video. I've got a 15-minute time limit that I'm up against. We've completed parts A, B, and C. In part B of the video, we'll continue on with parts D and E.